Okay, so the last example I want to run through for you very quickly is an infinite sheet of charge with a density of, this is a lowercase sigma of q over a. So sigma represents the density of charge in some area here. If you have an infinite sheet of charge, you can't tell what the whole charge is because it's got to be infinity, right? So you tell how much charge there is per unit area. So this could be like 3 nanocoulombs per square meter or something like that. And what that tells you is that if you mark off some area of the sheet, then it's got some charge. So, for example, here is, let's just say this is all positive charge, and I'm drawing little plus signs here, but you get the idea. So this is all positive charge, but it's it's spread out everywhere. Then you could draw like a little rectangle around part of this, so whatever, and say within the area of this rectangle, the charge is equal to sigma times the area. So this is just another way of re-expressing this, saying Q equals sigma times the area. Okay, so let me back up so I can get rid of the rectangle. Okay, so what we want to do is calculate the electric field around in an area near this sheet, or at any place near this sheet. And let's remember that the sheet goes infinitely in all directions. So these little arrows show that it goes infinitely in all directions. I had to draw this little rectangle worth of it, but it goes off in all directions forever and ever and ever. Uniform charge everywhere. So as you know, what we do is we construct a Gaussian surface around some fraction of the charge, and then use Gauss's law to construct, to determine the flux of the whole thing, and then we can find the charge on that little section and the electric field and all that. So the question is, what Gaussian surface should we use with this field, with this sheet of charge? And one thing you probably remember is that remember for Gaussian surfaces, you want a place where electric field vector dotted with n hat is constant. So we want to find bits and pieces of surfaces where this is true. Let's see, the electric field. So think about the electric field near this charged sheet. Say you're a distance, some distance off the charged sheet in a perpendicular direction. Does it make sense that the charge could go like parallel to the sheet, or there could be any component parallel to the sheet? I'm sorry, not the charge. Does it make sense that the electric field could be going parallel to the sheet in any way? And the answer is no, because if it was, then there's no reason for it to favor one direction along the sheet over another, because the sheet is symmetric. It looks the same in all directions. If you're standing on the sheet, there's no difference between looking north, south, whatever. So, so you would expect then that the charge would only go in or out. So we can actually, if we want to find coordinate axes here, we can say this out here. We'll call this our, let's see, what should we do to do, let's see, right-hand coordinate system, let's do x, y, and z. And so we can say on this entire sheet, it stretches in the y and z directions. And the electric field at any point is going to be equal to, some constant times I hat. And it might be positive, it might be negative, but it's going to be some constant times I hat. So, it's going to be pointing along the x direction. So, at this point, we just want to define, we don't want to find a volume that we can enclose. I'm going to draw in some electric field arrows, just to show the directions pointing. And so, if we want this times the normal for the surface to be constant, one of the rules we came up with is that surfaces that go always parallel to the electric field will have this equal to 0. And those are the best kinds of surfaces, because not only are they constant, but they're equal to 0, so adding them up is easy. So it doesn't take much thinking then to see that basically any surface perpendicular to this sheet is going to have E dot n equals 0. So we could, for example, draw a little box like that and say this box is extending in the x direction, or this rectangle is extending in the x direction and the y direction. So it's perpendicular to the sheet, and it's and then the normal vector for it is going to be like that, right? So that's n hat for this little square, and that's going to be dot that with 0. Well, n hat here is going to be k hat. I'm really sorry, fumbling around with my explanation here, but I hope you get the idea. So n hat here is going to be k hat on this little square, and something in k hat dot something in I hat is going to be 0. So that's going to work. So what you want to do actually is draw, basically make a bunch of fences, if you will. So each fence is sort of a, some kind of rectangular portion, or some kind of rectangular surface that is perpendicular to this sheet of charge, and then you sort of use these fences to box off some area. And so there we go, and I'm just going to draw little dotted lines in here for the stuff in the background. So I hope you get the idea. This is sort of a cube, or not a cube, but like a rectangular prism sitting on this area. Okay, so, and for all of these things here, for all these four sides that are, going front, back, top, bottom, the normal vectors, so normal vector there is going to be negative j hat, normal vector here is going to be positive j hat, and normal vector here is negative k hat. For all of these, the flux is going to be 0 because E dot n is going to be 0. So remember, flux through a surface, if E dot n is constant, is E dot n times the area of the surface. And so there is there's 0 flux through any of these four surfaces. So through this top surface then, what is the flux? Well, first of all, the normal vector there is positive I hat. So, and we know our electric vector there is our electric field vector is E times I hat. So phi for this surface here, phi for that surface is going to be equal to E I hat dot I hat times A. And since this is scalar, we can take this out. These are both scalars. We can take this out and just say I hat dot I hat is 1. So that's going to equal the electric field at that place times A. Okay, now here's the tricky part. What about the back side? What about this side here, the left side, the one by the sheet? How do we do that? Well, there are a couple different ways to do that. And I'm going to show you both of them and then pick one. So let's say this is our edge-on view of the sheet. So this, let's see, actually let me move it, let's see. Here's our edge-on view of the sheet, okay? So the y-axis is going up here, the x-axis is going this way, and the sheet is flat on towards us. And of course this is just a portion of it, okay? So if we draw it, the way I prefer to do it is to draw it like this, going all the way through the sheet. So this top side and the bottom side will have a flux of 0, right? Because your normal vector will be like that, and the electric field is always going like that, either towards or away from the sheet. I'm going to draw it going away from the sheet because our intuition kind of says that the electric field vector should be pointing away from positive charges. So I'm going to go ahead and draw it away from the sheet. And the normal vectors in these top and bottom ones are perpendicular. Same for the faces that are sort of flat on towards us. Those are coming out at us or going in, into the screen away from us. So those are also perpendicular to the blue. So all that really matters are these two sheets here, are these two faces here, the faces that face along the x-axis, or the faces that are parallel to this sheet. And so the way I do this then, the way I would recommend doing it, is to set this up, and if you want to be absolutely careful, this is just the easiest way to set it up. So there's your, we're going to make this a cube. So this is our Gaussian surface, it's a cube. This is still an edge-on view. So there's your y, and there's your x. And this is still a cube, so we're looking at a cube that sort of lets the infinite sheet of charge slice through it. Okay, so there's your infinite sheet of charge, and putting the little pluses on to signify this line has the charge on it. And then we basically take the cube, and we say the cube has, whoops, well, I'll do green for cube dimensions. So the cube has a side length of s. Here's the side length of s. Okay, and then it's s thick front to back. We can't see that, but it's s thick front to back. And we set this up so that the midpoint of this side is halfway through, or the midpoint of this side is what's on the plane. So by symmetry, then we can say the strength of the electric field here has to be equal to the strength of the electric field here in magnitude, right? It's facing the opposite direction, but they should have the same magnitude. So we can say here the electric field is negative E I hat, And over here, the electric field is positive E I hat. Okay, so here the electric field is pointing positive x direction. Here it's pointing the negative x direction. Okay, these are just the sides of your cube that are parallel to the plate. And everywhere else, the electric field is pointing, perpendicular or pointing parallel to the surface, so its dot product becomes 0. And so out here, of course, your normal vector is like this. Just to review, normal vector here is like that. And so what you do is then I'll call this like the left side and the right side. So total flux is going to be the flux for the left side plus the flux for the right side. Okay, and that is going to equal the flux for the left side. We take so on this side our normal vector is negative I hat, and on this side our normal vector is positive I hat. So in both cases, what we're taking is already on the positive side. We already did this. We found it was EA. On the negative side, you're going to have E times negative I hat dot negative I hat, and that's also going to equal 1. Okay, so this is going to be the flux through the left side is going to be E times A, and the flux to the right side is going to be E times A. And so what you get there is total flux equals 2EA, and that has to equal the charge inside here, which I'm going to say is Q. Okay, so Q, and then either we do divided by epsilon naught or times 4 pi K, and I prefer in this case to divide by epsilon naught. So what we get then for our infinite sheet of charge is that the magnitude of the electric field, well, let me not do the vector part yet. Okay, the magnitude of the electric field, we divide these through, is going to equal Q over 2A epsilon naught. And since Q is just lambda times A, and I erased the thing where Q over A is sigma, but Q over A is sigma, so the electric field is equal to lowercase sigma over 2 epsilon naught. And so then finally, if you want to do it in the vector form, you do electric field equals sigma over 2 epsilon naught. And then I guess if you want to give it you need to give it direction. I guess you could say like r hat and specify that if you're drawing, this infinite plane of charge or infinite sheet of charge, then r has to be some vector that's perpendicular. So you have to sort of pick the closest point to draw your r vector from. Okay, so point is that it's always going in the same direction, and this is a very powerful result. What this shows you is that the electric field from the sheet, if it's truly an infinite sheet, doesn't matter how far away you get from it, you still have the same electric field. And of course you can't have that in real life because you can't have an infinitely large sheet, but it does mean that if you have a large sheet of uniformly distributed charge, that if you're fairly close to the sheet, you will have a uniform electric vector no matter how far away you are from it, until you start getting to a decent distance relative to the sheet. So just for example, like if a sheet was this big, then you could say like right here and right here and right here would probably have about the same charge. And then, when you start getting a bit further away relative to the sheet, I'm sorry, about the same field at these points. I'm really not speaking well. I'm sorry, it's early in the morning. This is a crappy explanation. I hope this works for you. But then when you really start getting significantly far away, the electric field drops off. Okay, but anyway, the point is that's the result for a large sheet, that it's just sigma over 2 epsilon naught, no matter how far away you are.